Okay, so we'll just wait a couple of minutes until people join.
Mm-hmm. Okay.
But usually they're picking up very quickly.
All right.
Okay.
Yeah, so how's everything going with you? It seems like you're doing fantastic in Barcelona.
Yeah, it's good. Last results were good. Oh, by the way, we're broadcasting already.
Oh,
so we're
okay.
we're live.
Yeah, no more trading.
All right. I'm just waiting until the numbers catch up. So I think we were with Sandhill, we were close to 200. So I just wait maybe that these people are all back here. Yeah, this is the other advantage of online talk. I mean, again, there are strong disadvantages, but the other advantage is this, that looks like more people can join than in real life. Okay, I think we're already good on the participants. Okay, so let us then continue. Okay, and it's my pleasure to have Jeanie Lau from Ohio State University now as an experimental talk. And Jeanie is in Hong Kong right now, so it's a completely different time zone than most of us. And Jeanie will talk about flatbands in flatbands. Oh, in Flatlands. Okay, I'm sorry. Okay, thank you very much, Jeanie.
Okay. Right. Thank you. Thank you, Dima, for organizing the workshop. I thank everyone for coming to my talk. So this is definitely a different experience. I'm right now being in Hong Kong and being captive in a hotel room for 14 weeks. So at least this is a good way to pass the time. Okay, so, oops, oh wait, let me see if I can, okay, oops. Okay, so what is so the title of my talk, so flight band in Flatlands. You probably can guess what I'm going to talk about. So Flatland refers to, of course, 2D materials. So many of you have seen this figure, right? There's actually a pretty famous figure now from the review paper from Manchester group on 2D materials, saying we can stack 2D materials up as Legos. This, of course, is true. Right, but of course for Legos, there's only two positions you can make the stack, right? You can make this way and rotate 180 degrees. So my favorite analogy for 2D material is like they're fabrics. They're soft, they are stretchable, bendable, and you can make, you can have many different materials represented by all the different fabric colors here, and you can make arbitrary twist angles between them. So of course, the properties of 2D materials dramatically modified from the bulk. They're extremely tunable. And so as, for example, from Santil's talk, the previous talk, we see that, for example, even the Barry's phase or the Chern number are tunable. And so we can make artificial heterostructures and properties that are not easily obtained in the bulk. Okay, so what about flight bands? So what are flight bands? So, physicists will love interactions, may or may not be the personal kind, but at least definitely the electronic kind. So interactions give us many emergent states, for example, superconductors, quantum anomalous Hall, and charge density waves, ferromagnetism, etc., etc. So how do we get, so what's a flat band? The flat band is, of course, we know here, is just when you plot the energy as a function of momentum, we'll have very, it's a very flat plot, which means they have very small velocity, which is basically a slope of this plot. And in this case, so that the potential energy is much larger than the kinetic energy. Oops. So how do we achieve the flat band? So there are several ways to generate flat band. So one is in a magnetic field. For example, so basically given sufficiently large magnetic field, any two-dimensional system, regardless of the actual band structure, will become eventually flat. That is when we have the Landau levels of formation in a quantum Hall regime. Another is the stacking. Okay, we can stack up the, for example, the different number of layers to achieve flat band. So then I'll tell you a little bit about it. And of course, this being the emergent phenomena, the symposium on moire materials, I'm going to just tell you about, of course, we'll tell you about the twisting. Okay, so let me just tell you a little bit about the stacking. So of course, stacking, we have, so in this case, again, we are working on graphene, and in particular, we're focusing on rhombohedral stacking. And this is, so we know the monolayer graphene has this linear dispersion, and the bilayer graphene, the dispersion is quadratic. And this, in the tri-layer graphene, this is ABC stack tri-layer graphene, the dispersion is cubic. Actually, Santi also mentioned this briefly at the last talk. And also, then when you would go to 4-layer graphene, the dispersion is quartic. So you can see as we go increase the number of layers, at least in rhombohedral stacked graphene, the bands become flatter and flatter. Okay, so this is some of previous work in ABC stacked tri-layer graphene. It's suspended graphene with 2 gates. So when we observe a metal insulator transition, when we cool down the device, the transition temperature is about 35 Kelvin, and we measure the band gap of roughly 40 millielectron volt. And so this gap is actually pretty large. And this is unexpected from a single particle picture, which predicts the conduction and the valence band would touch at the point. And so that's the single particle picture will give you a semi-metal. But in this case, we actually appears to have an insulator with a gap of 40 millivolt. We will go to actually now ABC stacked tetralayer graphene, this 4-layer graphene. We actually seen a similar gap, except it's even larger, so up to 80 millielectron volt. And this gap disappears at large charge density, temperature, and electric field. So we think this is, again, likely a layer under ferromagnet at half filling. Okay, so this is what we think the phase diagram of is in the ABC stacked field layer graphene at the charge neutrality point. So it starts with a layer under ferromagnet. We turn up the parallel magnetic field, eventually becomes a ferromagnet. If you turn up the outer plane electric field, it becomes a layer polarized insulator. Okay, so of course these are all, so far this works, we in my group are done on suspended graphene, and of course recent work from Feng Wang's group, for example, in ABC stacked tri-layer graphene, they have seen a number of interesting phenomena, including correlated insulating state at half filling, and the quantum anomalous Hall state, and also evidence for superconductivity. I just want to mention that we do see some evidence of ferromagnetism. So in ABC stacked field layer graphene, a small filling. So if we go to a, we dope this insulator slightly, dope away from the half filling. We actually observe pretty prominent hysteresis as a function of magnetic field. Okay, so all right, so this is just a kind of very brief touch upon the how can we produce flat band by stacking in field layer graphene. Okay, so now of course we're going to tell you about the twisting. So this is I tried. Okay, so this is the outline of the this my seminar. So the first part I'm going to tell you about our work on the superconductivity and correlated insulating states in twisted bilayer graphene below the magic angle. And the second part of the talk, I'll tell you actually about our recent work in high mobility two-dimensional semiconductors. So this is, strictly speaking, what I'm going to tell you is actually not moire. yet. But if you stay to the end, I'm going to tell you why I think it's relevant for the moray, where I see some evidence. Okay, so all right, so let me start with the first part. Okay, so so this being the second week of this symposium, I probably don't need to go through all the introduction. So let me just go through this slides very quickly. So of course, with if we have a monolayer graphene, I put a second layer graphene on by the small angle, we form a moray superlattice, and the wavelength of this well, the period of this unit cell is given by this the formula here. Okay, so the theory, this seminal work in the theoretical front, I would say, so it's you know, I have this paper from McDonald's group and also several other groups, which this actually goes back in you know, 9 years ago, and they have predicted a moray band in twisted double bilayer, so twisted bilayer graphene. They predicted a magic angle of 1.5 degree with very flat band. And there are actually, I should point out, there's actually quite a few experiments in this area, some even before came out, even before this theoretical paper. But of course, so I think some interesting phenomena was seen, but I guess no, but somehow maybe the really interesting discovery, of course, was made by Pablo, the seminal work from Pablo's in 2 years ago, shows that there's this so-called mod, or now it's called correlated insulating state in twisted bilayer graphene at high filling when you have 2 electrons per superlattice cell, and when you dope away from the high filling, and you see the superconductors. So I think that's basically the discovery of a superconductivity is really you know, propelled this work instantly into rock star phenomena. Okay, so since then there have been a lot of rapid experimental progress, sometimes so much so I feel like it's almost difficult to keep up. So this is some of the work published in 2019, and then many more published this year. And now this twistronic has been expanded to twist a double bilayer graphene, twisting bilayer or monolayer graphene, and ABC stack trilayer graphene aligned to boron nitride, and twisted bilayer tungsten selenide, etc., etc. So this is really very exciting frontier, and with discovery it will come out almost monthly. Okay, so I just want to tell you about this our work in this area. So this work is so led by my student Emilio Codicido here in the clean room outfit, in collaboration with Mark Baccarat, also at OSU, and the theoretical calculation is performed by Fan Zhang at UT Dallas. Okay, so here we use the same tear and stack technique that has been pioneered by, for example, Tuto's group and also Pablo's group. So we start with single piece of graphene. We're coming with boron nitride break into 2, rotate one of the piece by a fixed number, and then stack the 2 so that we know that the 2 have the 2 pieces of graphene stacked at a well-defined angle. Okay, so this is, and this twisted bilayer graphene is sandwiched between hexagonal boron nitride. So here's a device image, and it's a device schematic. Okay, so you take this piece of graphene, we'll cool it down here in the helium-3 fridge. So this, oh, sorry. So this, I think, actually, this is taken in the pump helium-4 fridge. So this data is actually taken at 1.5 Kelvin. So here we have, we're plotting the resistance, longitudinal resistance of the device which is color. So the kind of the brownish white color corresponding to high resistance, and the blue color corresponding to low resistance. And so this is, we're plotting the color, so the resistance as a function of magnetic field and gate voltage. So this is so-called the Landau fan. Now we see a series of lines converging to several points on the at several points at zero magnetic field at different gate voltages. So the central one, of course, is a global Dirac point, and we can trace the this minimum in the longitudinal resistance to the central Dirac point, and this Landau fan had fourfold degeneracy. And then to either side of the global Dirac point are the secondary Dirac points, and so these comes from the mean Boulogne of the superledger cell, and they also, you will trace this Landau fan, they also have fourfold degeneracy. And we know the capacitance of our gate, and so from the basically the density at which a secondary peak occurs, so this is roughly 2 × 10⁻12 per centimeter square, we can calculate the twist angle. So here, theta is a twist angle, and A is the lattice constant of just the monolayer graphene. And so this gives us a twist angle of 0.93 degrees, which is actually pretty small compared to the magic value of 1.05 degrees. Okay, so so we can do some temperature dependence of these peaks. So we can see that actually the this peaks at okay, so I should see, so say that the this global Dirac point occurs at, of course, we have nominally 0 electrons on the device, and the secondary Dirac points on either side. So we have 4 holes, 4 electrons per superledger cell. So as the temperature increases in this particular device, we see that actually the peaks at 0 or at the full filling of the superledger cell are actually not strongly temperature dependent. But then we do see at half filling, so 2 electrons per unit cell, we do see another set of Landau fan coming in with the degeneracy of 2, and this is also consistent with other works in this other work in the twisted bilayer graphene. And here we see some temperature dependence of this peak. Okay, so what's perhaps a little bit more interesting is that we do see this as the temperature decreases to say 0.3 Kelvin, the resistance of this region, so it's slightly above 2 electrons per superledger cell, resistance of the region decreases to 0. Okay, so this, so I think we have a superconducting state here. Okay, so we can take a more detailed look at this region. So we just try to follow the resistance of this region as a function of temperature. So this is what we see. So we start out roughly about 1.3 kilo ohms, and then we have this kind of 2-stage drop of the resistance, and drops to 0 within the measurement error. And the TC is roughly, if you just look at this, the last stage of the drop is roughly 0.3 to 0.5 Kelvin. We can measure here we're measuring the voltage as a function of the bias current, which is vertical axis, and the gate voltage, which is which is horizontal axis. So the center here correspond to roughly the doping of 2.7 electrons per superledger cell. So here we're seeing that, so for example, the superconducting state, which have zero voltage, zero resistance here, which is represented by the black region, is outlined here. And here we're showing a couple of different line cuts at different density, and showing that we have the largest critical current we've seen is about 15 nanoamps. So this is actually quite a very small angle, a small twist angle in which superconducting state has been seen. Oops. Okay, so if we apply magnetic field, we can suppress the superconducting state. So the curve on the left here shows we have the resistance as a function of perpendicular magnetic field and gate voltage. And so if we increase perpendicular magnetic field, we can see that this zero resistance state, which represented by the dark blue color here, very quickly goes away. So the critical field is about 30 to 40 millitesla. In the parallel magnetic field, it persists a little bit larger, so to 0.5 Tesla. So the curve on the right shows the voltage current characteristic in different parallel field, and at 0.5 Tesla, the superconducting state goes away. Okay, so all right, so this is basically we're seeing that we have a relatively small angle device, and in this angle, and what we did see both a correlated insulating state and also superconducting state. Okay, so so far we have focused on the basically the first Born zone. So within the when we're filling our plus minus 4 per unit electrons per unit cell. Okay, so we can actually we can expand it just to larger density range. So here we're filling up to plus minus 12 charges per unit cell. And okay, so several interesting features occur. So first is that we can see that there's additional sets of Landau fans coming in at 8 and 12 charges per unit cell. So for example, here we're tracing the Landau fans at 8 electrons per unit cell. This gave us a tertiary direct point. Okay, and we our tertiary peak, and then we're also here we're tracing the Landau fan going converging to 12 plus minus 12 charges per unit cell, and this gave us a quantary peak. And both of these all of these peaks, so they actually fan out in both directions, and also they have a degeneracy of 4. Okay, so this is consistent with the band structure calculation performed by Fan Jiang's group at UT Dallas. So what they see is that, for example, they see actually a direct point. When you fill up, so in addition to the direct point of the first band, you actually have, you see the second, you also see a small direct point of the second band, and you go to third band, you see a direct point here. So this can explain the observation, for example, of this, this peaks at plus minus 12 electron per unit cell, and at this feature at plus minus 8 electron per unit cell, we actually do not see a peak at if we do not apply magnetic field, but we do see the features in the Landau fan. Oops. Okay. So and then now actually we want to bring your attention to additional feature here, which is this feature at 5 electrons per unit cell, plus minus 5. So they appear on both sides of of the global direct point. And they are actually, if you don't stay at say 1.5 Kelvin, they're actually not that obvious. So you can see a kind of a small peak here. Okay, we can barely see, which is this orange graph. But they are actually very prominent. For example, if you increase magnetic field, or decrease the temperature. So this, again, this line trace here are taken at 0 magnetic field. So decrease the temperature, this peak actually becomes very prominent. Okay, so then this, if we take the resistance of the peaks of both either on the electron side or on the hole side, and we fit it to the thermal activation Arrhenius plot, and this gave us a gap of roughly 1 Kelvin. Again, then this becomes more prominent at high magnetic field. And interesting thing is that the Landau fan, the degeneracy in this case is actually roughly 8. So it's so the data is not super clear, but we can extrapolate a few Landau fans to this particular state. This, for example, this peak here is a peak at 5 electrons per unit per superlighted cell, and we can extrapolate a few Landau fans to it. And this, and to the, to the best of our measurement, we believe the degeneracy is roughly 8. Okay, so so this is so from the band structure calculation, so it actually looks like there is actually a flat band region of the next band. Okay, so not just the first band is the lowest band is flat, but actually you can have a flat band even in the second band. So the large degeneracy we've seen so suggests that we not only have this approximate SU4 symmetry, but perhaps we also have emergent new symmetry. So, so this, I think this actually have not been reported before, and we think this, and this is a quite interesting observation. Okay, so just to conclude this part of the talk, I want to say that even we have a small angle, than the orthodox value, which is 1.05 degrees. We still have flat bands, and this is actually a smallest magic angle sample with a twisted bilayer sample with both superconducting and this correlated insulating state observed. So likely that its twisted bilayer graphene does not have a magic angle, but it probably has a magic range. And we also want to say that we can have, if we go, the interesting things and electron correlations can also happen at high density and go beyond the first band. Okay.
Okay, Jenny, we have we have a couple of questions. So first question is, can you explain why the second Dirac point on the right side is much more intense than on the left side? So basically electron hole symmetry.
Yeah, so I think it's, yeah, so I think it, well, okay, again, I did not do the calculation, but I believe it comes from the fact that there is, so that it's not super asymmetric, but there's, I think, slight asymmetry comes from the electric field that leaves, that will break the electron hole symmetry. And this is a single gated device, so we have only a back gate. And when you dope the device, it also introduces electric field.
Mm-hmm. And then the second question is whether, so the question is whether at 0.9 degrees, reconstruction effects, so basically lattice reconstruction strain effects have to be taken into consideration already.
Ah, that's a good question. I think it maybe. we do not know. I think this is a case where collaborating with microscopists will help to understand.
But I guess it's still, I would guess it's at much lower twist angles that it really becomes dominant. Whereas, well, even at magic angle, one has to take it into consideration to observe the band gaps. Okay, so and then one question was about the thickness of boron nitride. So you have a local gate, right?
Yeah, we have boron nitride is actually fairly thin. Actually, I cannot remember the top of my head, on the order of 10, 20 nanometers. So we have a graphite gate below the boron nitride. Yeah.
Okay, I think that those are all the questions.
Okay. Okay, so all right, so yeah, so let me move on to the second part of my talk, which is tunable spin-orbit coupling in high mobility 2D semiconductors. So this work is unpublished. And so most of this will be just tell you a recent experimental result in this case, in this device. And then towards the end, I'll tell you, why we think it might be interesting for Maury phenomena. Okay, so we know that, okay, we're starting with graphene. Now, isolation of graphene is 2D materials. Now we have the whole slew of 2D materials, from semiconductors to superconductors to charge-density waves to ferromagnets, antiferromagnets, etc., etc. Okay, so, but so now we actually want to focus on spin-orbit coupling. So let me just give a brief introduction to spin-orbit coupling for the students here in the audience. So the twofold degeneracy of spin is actually protected by the combination of time reversal symmetry and the inversion symmetry. So if we want to achieve the spin splitting in a crystal, you can achieve it by breaking the time reversal symmetry. For example, we can apply external magnetic field, and this gives you the Siemens, for example, Siemens splitting of spin. Alternatively, you can break the inversion symmetry of the crystal, and this coupled with a spin-orbit coupling and will produce a spin splitting even without a magnetic field. Okay, so what is spin-orbit coupling? A spin-orbit coupling is a relativistic effect. So if you have electron, for example, moving in an electric field, in this case would just be electric field of the crystal. For example, you have electron moving around the nucleus. They will experience the effective magnetic field in the rest frame. So in the rest frame, this is what the electron thinks. So from the electric field between the electron and the nucleus will look like a magnetic field to the moving electron. So this is basically a spin-orbit coupling in a nutshell. So there's the spin-orbit, so now there's a word called spin-orbitronics, and actually so spin-orbit coupling can be used to engineer a number of topological or spintronic devices, for example, spin-orbit torque, spin-orbit qubits, minonics, corner spin Hall effect, etc., etc. So there's a nice review article from this in the Nature Materials in 5 years ago. But of course, the community always have a sort of love-hate relationship about spin-orbit coupling. So on the one hand, spin-orbit coupling is very useful and can be, and you engineer to tailor a number of all these phenomena. On the other hand, a spin-orbit coupling introduces scattering, which will reduce the spin lifetime and electron lifetime. And so, so the question is, can we have? So what do we do, right? One, can we have the best of both worlds? The answer is you can, if we can control the spin-orbit coupling in situ. And so this, of course, brings us to 2D materials. Like everything else, you know, the spin-orbit coupling turns out also tunable in 2D materials. So in this case, we actually focus on the metal chalcogenides. So these are the family of layered semiconductors. You have, for example, includes materials such as indium selenide, gallium telluride, indium sulfide, etc. Okay, so and each layer consists of 2 metal atoms. So for example, the indium, sandwiched between 2 chalcogen atoms, for example, in this case, selenium. So if we view it from the top, you actually do have a honeycomb lattice. With the metal and the chalcogen occupying the sublattice, each of the sublattice sites. They have a thickness-dependent band gap ranging between 1.3 electron volt. And in contrast to transition metal dichalcogenides, so these metal chalcogenides have a direct to indirect band gap, transition, meaning they have direct band gap in the bulk, and it becomes indirect in monolayers. So they actually have high mobility demonstrated by, for example, the Manchester group. They have observed a mobility of the reported mobility of 10,000 in indium selenide. And interestingly, there is also a prediction of half megahelix state will appear if we are able to dope the metal chalcogenides, you know, will highly hold dope it so that this we can achieve 100% spin polarization. Okay, so there's many reasons for wanting to for studying the metal chalcogenides. For example, the direct band gap, apart from monolayer, so even in bilayer they will have a direct band gap. So this is good for optoelectronic studies. If we can achieve this 100% spin polarization, that will be also, you know, great for spintronics devices. Okay, so this is that's our motivation, and all right. So now to the experiment. The experiment, we start with the bulk crystals, which are grown by the Luis Balisca's group at National High Magnetic Field Lab using the Bridgman method. So this is a picture of the bulk crystal. It's actually a pretty large piece of crystal, and so the indium selenide actually have several, actually have 4 different phases: alpha, beta, epsilon, and gamma phases. So they're corresponding to different stacking. The crystal grown by Bridgman method, it has predominantly gamma phase, which is actually rhombohedral phase, but the stacking fault and twins are actually pretty prevalent. So for example, here are some TEM images of the bulk crystal, and here we, you know, if we see where the bands are bright area, actually the good crystals, which means they have the rhombohedral stacking. And whenever you see the dark lines, these horizontal lines here, they correspond to actually stacking fault or twins. And so here are some TEM image. To the left is the TEM image of a twin, and to the right is this side view of a stacking fault. Okay, so we take this crystal and we exfoliate it to make our devices. So indium selenide is not that stable in air, so we exfoliate and transfer inside a glove box. We contact this indium selenide by graphene, field layer graphene, and then we sandwich everything between hexagonal boron nitride. So the indium selenide we study range from bilayer to about 10 layers, and we put 2 gates. So we have a top gate and a back gate, so that this we can independently adjust the charge density and out of plane electric field. Okay, so here's some transport data. We're plotting again longitudinal resistance as a function of back gate and top gate voltages. We can take some line cut, and so here shows how the resistance change as a function at different back gate voltages. So the record mobility, so the mobility, the field effect mobility is roughly 5,000. And we can see that the longitudinal resistance respond to both gates. And so this tells us we have a single layer of electron gas, as opposed to a wide quantum well, which can have 2 layers of electron gas. So here we only see evidence of a single layer of electrons. All right, so now we can put on the magnetic field and study the fan diagram. For example, here we have a 6-layer device. We see a very nice fan, very nice Landau fan. Here's a 2-layer device, also very nice Landau fan. This with Schubert-Hasse oscillation starts at about 3 Tesla. And if we take the oscillation amplitude and plot its dependence as a function of temperature, using the Lifshitz-Korswich formula, this gives us, we can measure the effective mass, which is about 0.14, and this is consistent with previous data, previous work. Okay, so all right, so now so far so good, right? So far this is actually looking all very normal, but actually, if you not so normal, if you differentiate this graph. Okay, so if we differentiate, so here we're plotting the differentiated curve. So the differentiate with respect to magnetic field. Then we actually see, so this is actually this is actually a 4-layer sample. What we see here is actually there's some strange phenomena. Okay, first is that we see this kind of white region corresponding to basically 0, meaning the amplitude of oscillation. So again, it's differentiated. So the amplitude of oscillation is very small in this white region. Okay, so if we take a line cut, we can see this oscillation. Basically, looks like we have beating, right? So we have node here and we have node here. Okay. Another thing is that if we say take this region and zoom in, and what we see is that this this red curve here, which corresponds to the maximum, after crossing this this white region, which is the node, it becomes a minimum. But then if you count the degeneracy of each of this fan, they still have 2-fold degeneracy, which means that, for example, before this node, we will have only integer states resolved. And after this node, we have odd states resolved. Okay, so which is actually quite strange. Okay, so, and if, so let's see if we just make the Fourier transform of our data, we do see, so this just clearly we see 2 frequencies here. Okay, so this just tells us our oscillations have 2 different frequencies. Actually, you can directly see from the, for example, the beating, right? That's the signature of interference of 2 frequencies. And this tells us we have 2 Fermi surfaces. So what are the 2 Fermi surfaces? This actually, since the indium selenide, we actually do not have valley. Actually, just have the next candidate. The only candidate is really spin. So basically, we have spin splitting in this case, but it's not just your normal Siemens splitting, because Siemens splitting, the degeneracy should change from 2 to 1, but we actually retain the 2-fold degeneracy in either case. Okay, so another observation we have is that if we change the electric field applied. So here we're actually, so this data is taken at a constant electric field. of 0.33 volt per nanometer. And if we change the electric field to 0, okay, so this is not maintaining 0 electric field across the layers, and take the same Landau fan, we can see that the node has shifted to a different spot. Okay, so it's for example, it's a line cut here. So we can see that basically this beating feature can be changed by the electric field. Okay, so all right, so so how do we explain this? So it turns out that this, so the beating feature is actually, tells us we have basically we have a spin split bands. And the fact that it can be changed by the electric field is a signature of Rashba spin orbit coupling. So again, the brief introduction, to the Rashba spin orbit coupling. So what is that? So here we're starting with just a normal band, right? So energy as a function of momentum, and we have so it's spin degenerate. It's your run-of-mill garden variety parabolic band with effective mass m star. Okay, so if you add the Rashba spin orbit coupling, which have this form here, this alpha is the so-called Rashba parameter, which tells you how big, how strong this effect is. And this sigma is here, it's just a Pauli spin matrix, and P is momentum. And you solve the Hamiltonian, this will give you the energy. In this case, is a 0 magnetic field without any magnetic field. So basically what you have is you have this linear term plus minus linear term in momentum, and with a coefficient that is this Rashba spin orbit parameter alpha. Okay, so what you have is basically you take the band and it splits into two like that, okay? So, so basically, in this case, therefore, you have 0 field spin splitting. So, of course, that's a cartoon figure. Well, so a little bit more realistic cartoon figure is like this. So you have basically so this arrow here indicate the spin direction. So the spins are in plane. So the one is going clockwise, the other is going counterclockwise, and they are spin split. Oops. Okay. So now we can, with this in hand, we can understand our data. So for example, we can, if you solve the, so actually Rashba in the original paper have solved this in the presence of magnetic field, and this is, and this gives us the Landau level spectra. Okay, so here we plot, oh, I should say this. So here we're plotting, so we can plot this Landau level spectra. So this is from for the two, one is for the spin up band and the other is for spin down band. And see, we can see that now we have a series of Landau level crossings, and that correspond to the to this node. And what you also is that we can understand that why we can see this kind of even to odd resolved transition, which because combined with the Landau level broadening, so when we cross the Landau level, for example, so here maybe this is here we are maybe resolved even, and that's, for example, when we cross the Landau level, when the two bands cross, spin up and spin down bands, Landau level cross, then can produce this even to odd integer state transition. Okay, so this is a simulation we made, for example, with some realistic parameters, so that we can see that now we can, of course, this is assuming 1 milli electron volt Landau level broadening, so we can reproduce the data, at least the main features fairly well, and in particular we can we can reproduce this transition from the maxima to minima, for example, after we cross this node in the oscillation. Okay, so another nice thing about this being able to observe a beating in the quantum oscillations is that we can directly extract the Rashba parameter alpha from the data without any fitting parameter. So a little bit more detail is that this basically the product of the effective mass and alpha is given by this equation here. So apart from the constants, all you really need is this delta n, which is basically difference in density of the two of the spin up and spin down populations, and that can be directly extracted from the beating frequency. And this n is average density of the spin up and spin down. So basically, the delta n is n up and minus n down, and this n is just average of the two spin species. So all of these we can actually we know, right? We can obtain this from the data, and this m star here also we obtain this from the temperature dependence of the oscillations. So now actually we can extract alpha without any fitting parameter. And so this, for example, in this, we can say that in this particular data set, alpha is roughly 0.9 times 10 to minus 11 EV meter. And this is actually a fairly large number, even though this looks like a kind of a small number. Actually, I should say this is actually a fairly large number. For example, in indium arsenide quantum wells, this will be 0.2 or 0.1. Okay. All right. So now we see that. Okay, so we can directly measure alpha. Now we want to say how it can be changed by the electric field. So again, this is a nice thing about the 2D materials that we can directly control the spin orbit parameter. So ideally, we can take this type of data, at every electric field, but a little bit more time efficient method is we stay at a constant magnetic field and we change the charge density and the electric field. Okay, so then we can actually, so now we see that, so this is again actually differentiated longitudinal resistance. What we can see is that the, again, we have this, we can see this transition, right, from R to, from base maximum to minimum and vice versa. And this transition point kind of almost linear, but not quite, but approximately linear moving, on this plane of electric field and charge density. Okay, so we actually can basically by fitting these transition points, we can and using this just this Landau level spectra, we can obtain how the spin orbit parameter change as a function of electric field. So here we obtain this is experimentally this is obtained how the dependence of alpha on electric field, and this alpha 0 is 0.6 times 10 to the minus 11, and this is we call it alpha 0, which is the intrinsic Rashba parameter of this device. And then you apply electric field, and so this will tell you how tunable this parameter is. So here we have a coefficient 1.2, and the electric field is in volt per nanometer. Okay, so now we can do this for all our devices we have. So in particular, we actually have made devices on flakes with atomic steps. so that we can see how the Rashba parameter and how its tunability systematically change with sample thickness. So for example, here we have, here we're showing a flake image of, you know, we can see all these atomic steps, which have 6, 7, 8, 9, and 10 layers. And here we can do an AFM scan across one of the, you know, across this, you know, on the step, and we see that the height difference is 0.8 nanometer, and that's correspond to basically 1 indium selenide unit cell. So because it's basically, again, remember each unit cell thickness has 4 atomic layers, so it's covalently bonded. So 2 indium atoms and 2 selenium atoms. So the unit cell is about 0.8 nanometer thick, and which is what we see across each of the steps. All right, so for this case now, in this particular device, we have 7, 8, and 9 layers, and we, you know, we perform the same measurement. Again, we measure the resistance as a function of electric field and charge density, and we can see that this transition point, again, that's where they switch from maximum to minimum, and systematically change as a function, as the number of layers increase. So namely the shift to more negative values of the electric field. So we can capture that in our simulation, and from this we you know, obtain the dependence of this Rashba parameter on the electric field for each of the thickness. Okay, so here this, okay, so this is just to summarize what we've seen so far. So in these devices, we can, so we basically this alpha, we plus alpha, this Rashba parameter as a function of the electric field. And this is just using this parameters we obtain from the fitting. And so they actually can be tuned over a large range. So roughly say between 0 and you know, 1 to 2, 10 to the minus 11, 11 eV per meter. And actually, in particular, this actually can be completely suppressed to 0, right? So you apply just enough electric field, we should be able to completely suppress it to 0. And so that's nice. So which means that with gates, we should be able to define regions where we make the make the spin orbit coupling go to 0, and some region we can make it large. And so this will be great for making spintronic or spin orbitronic devices. So here are the sign of this alpha. Here some are negative and some are positive. And so this just depends on the orientation of the lattice with respect to the electric field. So this is a bit random because when we exfoliate the flake and how we define the and drop it on the you know, on the chip, and so this therefore the sign of this alpha can be positive or negative. But the important thing is to you know, we can realize that we can basically we can have actually very large control, large range control of the electric field between 0 and some large number. Okay, so lastly, I want to say that in one of our devices, we actually see a anomalously large spin orbit coupling. So this is one device where, again, we're doing the same measurement, measuring longitudinal resistance as a function of electric field and charge density. And here, now we see instead of, for example, single transition in other devices, we actually see multiple transitions. Okay, so this can only be explained by the fact we have both very large intrinsic spin orbit coupling and also large tunability. So we actually do not have a super good explanation for this. We think they could be stacking dependent. And another possibility is that they indicate the DFT calculations from my colleague Wolfgang Windows group. So indicate the alpha, this is very sensitive to interlayer spacing. So as shown here. So if we just change the this interlayer spacing, so this is in angstroms, by just a few percent, we can actually change the spin-orbit coupling, by a factor of 2. So, so that's also maybe a mechanism for that. So, but I think it's actually interesting that it can be changed by such over a large range. And again, this is it's a good news for this for designing with gate-defined spin-orbitronic devices. Okay, so lastly, all right, as I promised, I'm going to tell you why we think it's interesting. And we for the Moiré, try to bring for the Moiré materials. This is for this symposium. Try to stay a little bit more relevant for the symposium. So in what I have shown you mostly so far are the differentiated data. So a lot of times in the if we differentiate with respect to the magnetic field. In the raw data, we actually see some strange features. For example, this is a 4-layer sample. We see features, which are these vertical features here. Okay, so if we, so this, this diagonal features are the regular Landau fan. Okay, but so which are these, which appears actually a higher magnetic field. We then actually low feature before the Schubert-Haas oscillations appear, we actually see this kind of vertical features, and they're actually periodic in 1/b. Again, we can actually do a Fourier transform where we can extract this this period. So it's roughly 10 to 20 Tesla. And this and here we're just plotting two line traces resistance a function of magnetic field at different top gate values. And we see that as Schubert-Haas oscillation on top of Schubert-Haas oscillations, we see this this oscillations actually are even lower field before the Schubert-Haas oscillations start, and they are independent of density. Okay, so we can, so this is a 2-layer sample. Again, we see this Schubert-Haas oscillation superimposed on top of the this density independent features. If we increase the temperature, they actually persist to very high temperature. So this shows that at 30 Kelvin, the Schubert-Haas oscillations disappears. But this, but this vertical density independent oscillations persist. Actually, it persists up to 60 Kelvin. Here, like 60 Kelvin almost disappears, but you can see there's a little bit, just still a little bit, you can still see a little bit. If you differentiate the data, you can clearly see that they are still there. It almost disappears. Okay, so we can observe this oscillation between 0.3, so at 0.3 Kelvin, which means it's probably not phonon related, and it persists to up to high temperature, which means that it's not Schubert-Haas, it's not the Schubert-Haas oscillation. So now what is this, right? So one possibility, of course, is that we already have a Moiré in this system, perhaps from the maybe a small interlayer rotation from either the all the interlayer strain, either from the fabrication or from the bulk crystal. So this thing is definitely interesting thing to explore. Okay, so just to summarize this part of the talk, we have tell you we have a spin orbit coupling in atomically thin indium selenide is actually quite large. And we can measure that directly without fitting parameters of the spin of the Rashba parameter. We can tune the spin-orbit coupling by gate over a large range. So I think very excitingly, we can really make it 0 in regions where we don't want a spin-orbit coupling. But in regions, for example, we want long spin lifetime. And we can make it large in regions where we want the spin-orbit coupling. For example, when we want to make quantum spin-orbit torque devices. And so I think this is this is interesting. This is great for the spin-orbitronic design. And lastly, we do see the density-independent oscillations, which we currently again do have not pinned down an explanation yet, but I think it does at least suggest the possibility of interlayer Moiré. Okay, so again, trying to stay on topic of this symposium, can we make flight bands in twisted indium selenide? Perhaps there will be correlated states. And one, I think, very interesting possibility is that we can have, for example, Moiré Rashba spin orbit field for spin orbitronics. Okay, so I think, are there questions here?
So there are a bunch of questions, but I think I'll wait. If you have a couple, yeah.
Okay. Well, I'm actually just finishing up. Yeah. So I'm just saying that 2D materials is great. We know that from Phil Anderson. What he says. This is like almost 50 years ago. That more is different. And I think this is later we know that small is different, and now Bhaskar and Khan face that the Moiré is also different. I think so. 2D materials have all of this, so that's great, and that's why we have this symposium, right? But I think the experimental challenge, as we see for twistronics, I'm sure there's many challenges. Both theoretically and experimentally. I think for example, one thing is that the so-called one sample publications, of which my own group is guilty of. I think this is actually a pretty, so I think it seems to have been somewhat common in this field. And but this is just experimentally we know that it's hard to make the sample at exact same angle again, and it seems that some of the features might be sensitive to the angle. So how do we control the angles precisely and reproducibly? I think that remains a challenge. Another is the sample uniformity. Of course, I think in the early days we've seen the samples that it can vary by the twist angles. Across a sample, by measuring different pairs of leads. But I think Dima Avatov's group, for example, have at least contributed greatly to this field by producing samples of very large angular uniformity. But still, I think some more recent work shows that, for example, from Pablo's group, shows that even within the same pair, within the same sample, you see this small sample variations spatially. Even though you might see that globally, you can see the transport indicate the angle is about this, is the same, but you might still have small angle variations within the sample spatially. Another challenge is that how do we disentangle effects of these all these various factors that can contribute to the phenomena. So we have disorder, you can have screening, you can have interaction strength, which changes by screening and changes by the angle, etc. Right. And the observation of superconductivity, apart from in twisted bilayer graphene, could be a little bit controversial. And so what would be an equivocal evidence for superconductivity, right? For example, is a decrease in resistance, a sharp decrease in resistance enough? Do we need to have, is zero resistance enough? Or should we have some sort of, for example, hallmark superconductivity, such as Meissner effect or microscopic coherence to prove that? Of course, lastly, you said, can the wafer scale twisted bilayer be created with uniform angle? All right, this is the twisted bilayer, of course, is not a thermodynamically stable state, but can they be grown? Right, if they can be grown, I think that would be great. But so I think sounds like very difficult, but throughout the years I've learned my lesson. I think I have to never doubt the ingenuities of the material growers. I think they, over the years, they come up with really clever, very clever solutions and creative approaches to everything, to the growth. Okay, so with this, let me just say that it's we have many materials that we can twist, and we have limitless opportunities and combinations. So I think it's a really exciting area. I want to again thank the organizers for organizing the workshop. Let me thank my student. So the work on the twisted bilayer graphene is led by Emilio Codicido, and the work on indium selenide is led by my student Dima Shcherbakoff. And my collaborators in particular, so of course, Taniguchi group, I provided the hydrogen brown nitride, and Wolfgang Window did the DFT calculations, Fan Zhang did the calculations band structure for twisted bilayer graphene, Baccarat's group did the experiment together, and let's see, so, and a bunch of people from the National High Magnetic Field Lab for the crystal growth, for the high magnetic field measurements, and for the TEM characterization. Okay, so with that, thank you for your attending the talk.
Okay, thank you very much, Jenny. So we're exactly almost at the end of the time, but let's
Okay.
have a couple of questions. Maybe somebody from the audience can raise their hand. Okay, so otherwise there were a couple of questions during the talk, so I can just read them off. So this is particularly about the indium selenide. So one question is with Evgeny Redekop is whether the two frequencies in the Shubnikov-Das oscillations can indicate that you have two different phases of the material.
Two different phases. That's interesting. I would say probably not. I guess if, say, graphene is any indication, if you have, well, that's interesting. I don't know. But I would say, okay, so firstly, if you have two phases, it seems unlikely that the frequency can be changed in such systematic way by electric field.
Mm-hmm.
Yeah.
Mm-hmm. And also, it's just too repeatable of a signature for different layers that it could be just.
That's right. Yeah.
Okay, another question is, right, is the measured Rashba spin-orbital coupling expected to change with the number of layers?
Yes, I would say, simply speaking, yes. I think the so-called intrinsic spin-orbital coupling is expected to change. Although I think there has not been a lot of theoretical calculations in this. In this one calculations I do find they actually, unfortunately, predict the opposite trend than what we experimentally measure. But short answer is yes, they should change. The long answer is that the trend right now does not agree between theory and experiment.
Okay, and I have a personal question. So for the rhombohedral graphite.
Yep.
So I probably missed it. Can you explain again how stable the system is? So basically, is it naturally occurring or?
It's naturally occurring. So we find that it occurs about 15% of our samples. I think the tricky thing is what we do find is that, so we basically image them and then suspend them. What we find tricky thing is that when we try to put it down on boron nitride, they very often change into ABA.
Okay, so they just somehow they can just relax back to, or they can just change the ABA state.
They seem to like to change the ABA state.
Even like really thick layers.
Oh, we have not tried really thick layers. I think we try maybe up to 4 layers.
Okay, I see.
Yeah.
Okay, I think we need to close the session. So there will be. Thanks a lot, Jeanie. Again, thank you very much for the talk. And we will come back in about 10 minutes. And again, we have the hot topic session with short talks by students and postdocs. So hopefully to see most of you in 10 minutes. Okay.
Okay, thank you.
Thanks. So.
Thank you very much. Thank you all. Thanks for the seminar. And I'm going to end the meeting now, and I will see you in a few minutes for the next session.
Okay.
Okay.
Bye-bye.
Thanks a lot, Jeanie.
Thank you.
Bye.
Thanks, Lima.
Thanks, Jeanie. Bye.